My pleasure today to introduce Olawale from Los Alamos National Lab. Been working with myself, Aaron Thomas, and Steve Bruce for the past couple of years now. He did a pre-PhD program in Earth System Physics in Italy, did a PhD in Ocean Science Engineering at Georgia Tech. During that time, he started working with us here at Los Alamos on a wave modeling as well, but on GPU porting of WaveWatch 3. Has since done some nice work in analyzing how ocean surface waves impact the coupled system, in particular related to the MJO, and now has been getting into machine learning for ocean wave emulation, which is what he'll talk about today. So I'll turn it over to you.
Yeah, thank you. I'll just go straight to the talk. AI for ocean surface wave emulation. Why do we care about surface waves? Wind-generated waves play an important interfacial role in the global coupled earth system, influencing ocean mixing, extreme momentum transfer, and coastal processes like flooding and sediment transport. The wave also interacts with sea ice and breaks sea ice. Accurate prediction representation of waves is actually crucial for protection of several offshore activities, such as the energy infrastructure, protection of lives and properties of coastal community. As you can see here from the news headline, that waves are really important. We need to care about them. Yeah, the question at the top here is showing the wave propagation equation in spectral wave numerical models. So instead of solving individual waves, spectral wave models solve the distribution of energy in frequency direction spectrum, driven by the various source and sink terms. Like we have the wind input, which had the energy, we have the dissipation source term, we have the non-linear wave interaction, we have so these are the ones we consider when you are dealing with deep ocean. So depending on the physics and where you are in the ocean, you probably need to consider, for example, if you're in the shallow water region, you need to consider wave bottom interaction. And when you're near sea ice, you consider wave sea ice interaction. Our focus here is the non-linear wave interaction. Compared to other source and sink terms, which actually add or remove energy at a particular frequency, nonlinear wave interaction redistribute energy within the wave spectrum, frequency spectrum, thereby important for the evolution of the wave. However, the exact computation of this nonlinear interaction is really expensive, and it requires solving a six-dimensional Boltzmann integral. And this is really extremely expensive, and it has been computationally optimized over the years. And the gold standard in wave model is called the Web Resource Tracing method, called the WRT method. And even with this, it's actually still 100 times more expensive than the rest of the model. So current wave model uses an approximated method, which is called the discrete interaction method, the discrete interaction approximation. This actually considers just a fixed wave configuration interaction. So you consider that the wave number 1 and wave number 2 are equal, and then they are different from wave number 3 and 4 by their magnitude, and consider that the interaction is happening at a particular angle. You can see from here. However, the approximated formulation, which is the DIA, sacrifices accuracy for speed. It's actually very fast. It is very, very, very fast at the other component of the wave model, but it sacrifices accuracy for speed, and several efforts has been made over the past years to actually improve the accuracy of the wave of the DIA. But this actually leads to the slowdown speed. Yeah, I'm showing the global mean of nonlinear interactions simulated by DIA, the WLT, and the difference between them. And you can see here that the DIA simulated high values of nonlinear interaction, the WLT, and this leads to high wave spectral energy. This is the figure showing the root mean square error of significant wave heights for the two methods relative to observation error 5. What you can see here that we have high biases with the approximated method, the DIA, especially in high wave activities. We can see from here. So our goal here is to see if we can develop a neural network emulator that achieves the accuracy of the WLT and the speed of DIA. However, several, in the past, I've tried to use ML to do this, and the last study was done in 2014. And I'm just going to summarize, they were enabled to actually get a stable model. I'm going to summarize why. The first problem is like they used a shallow ML model, some with just one layer, and and also the global no global training data set. They just assume like parametric training set or just a particular location like a lake or something like that, and also have a limited temporal coverage, just considering just 1 month. So we'll be doing so many things differently, and we show how we obtain the first stable nonlinear interaction ML model. First, we use a training data from a year-long global wave simulation. From WaveWatch 3, we first, this is a wave-only simulation, we first the model with globe winds. And then for the training data set, we use 2010 winds, and for online validation, we use 2020 winds. Simulation are done with both the DIA method first and other set of simulations with the WLT. We also compare our results with ERA 5 wave analysis, but one thing is ERA 5, the wave model in ERA 5, the ocean wave model uses DIA as the nonlinear wave interaction parameterization, but no, this is actually combined with satellite observation. So another thing we did compared to other studies actually just use the spectral wave energy or the spectrum as the input data for the ML model. We included additional inputs like the depth and also the group velocity. And also for our data selection, we like instead of using the entire globe, we chose a subsample to represent different diverse dynamical regime, high and low wave activities that you can see from the boxes here to represent high and low wave activities regions. Another thing we did is nonlinear wave interaction in WaveWatch has values that ranges from the order of -25 to -2, and we had problem training with such large range, and so we wanted to know the important values. So we conducted sensitivity tests, and we found out that values less than order of -8 are not important, and we only selected range between -8 and -2 for the training. And also in WaveWatch, instead of using the spectrum energy, WaveWatch actually uses the action density because this actually conserved energy in the presence of current, ocean current. And also, instead of using frequency direction space, they use wave number direction space. So we converted this from action density to frequency to spectrum energy in frequency direction. We're going to show that this conversion is actually very important, and we're also going to show that this additional input is also very important. We also tried different normalization strategy, but at the end we normalized the spectral variable using z-score normalization along the frequency direction beam and use a global normalization for the depth and group velocity. So this is just showing our training data sets and for the nonlinear interaction and that of the spectral energy. Like I said, the other time the difference, the DIA has high values of nonlinear interaction, and this actually leads to high wave spectral energy simulated by the DIA. For evaluating the performance of our model, we use the root mean square error metrics first in the frequency direction space, and after that we took the integrated spectral errors. That's what we use to evaluate this, and also for the mean wave parameters, we use the root mean square error. For the ML training, we also did something different by using a customized loss function. We weighted the mean absolute error by the standard deviation of the output, and this is the standard deviation of the nonlinear interaction. As you can see, between 0 to 250 spectral mean, we have high variance, and using this, it allowed the model to learn better small values in this high variance region by penalizing using the standard deviation. We're going to show that this actually improves our ML model also. And we decided to use the deep neural network. We tried with FNO, we tried with CNN, but since the deep neural network is doing the work and the inference time is good, we decided to just go with the deep neural network, and we did a little bit of parameter search with the deep neural network. We started from 2 layers to 6 layers, and from 512 neurons per layer to 4096 neurons per layers. What you can see here that is obvious is that when you go along the layers, the performance gain is smaller than when you increase the neuron per layers. So we decided to choose 480 layers with 3,700 nodes per layer based on the online performance. So we could actually use 2 and 3. The model is actually still better than DIA, but the accuracy gain is more than the computational gain. So we didn't gain so much computational time using 2 or 3, so we just stick to 4. So this is the loss curve for the selected model. We can see we are now over training. We did 300 iteration. And on GPU, with a single 800 GPU, our training time is just 6 hours. And for the online inference, integrating the ML with WaveWatch, we use FTouch. And for online inference, like I mentioned earlier, we are using the year 2020. We trained with the year 2010. We are using the year 2020 as the online validation. We also have offline results, but due to time, I will not be showing that. So first, we examine the stability of the ML model and its ability to spin up the wave model from a cold start. So one thing here is that for the training, we excluded the spin-up period. And with that, our ML was able to spin up the model correctly from the cold start. What you can see from here is that the WLC and the ML model closely match each other compared to the DIA, and we were able to spin up the model correctly, and we have a stable ML model. So this is showing the online performance and then the main parameters, the mean of the nonlinear interaction. This is the WLT, yeah, the mean nonlinear interaction, and the second figure is showing the difference between the DIA and the WLT, and then the figure C is showing the difference between the ML and the WLT. You can see from here that the ML error is smaller than that introduced by the DIA, and the pattern correlation from the bus number here is improved with the ML method, which shows that our ML model closely matches the pattern of the WLT and with reduced error. And the last figure here is showing the direction integrated spectral nonlinear interaction. We can see that there's a shift, like a large shift between DIA and WLT. But when you compare that with the ML model, our ML model closely matches the peak. And also at the tail here, we can see that our ML model matches the tail of the WLT compared to DIA. And the second figure here is just showing the spectral energy. We just can see directly that the difference between the DI and ML, we have this high values positive bias of spectral energy, and then this is really not showing in the NML in the model. We have better pattern correlation, and you can also see from the integrated spectral energy that our ML model matches the WLT compared to DI. Now I'm showing the spectral errors, the spectral integrated error from the error matrix I showed earlier. The top here is showing comparing the DI with WLT, and we can see errors in the high wind regions and also especially in the Southern Ocean. And the mean error, the mean global error is like 0.8 or -7. But when you compare with the ML model, you can see that at all regions that we have a reduced error when using the ML model, and then the mean global error reduces by almost 50%, and our ML model is doing better. And this is the same for the spectral energy, and you can see that using the ML model we have like a reduced bias compared to the DIA. So the online performance, we're talking about the mean wave interaction and then the mean wave parameters. And first, you're just looking at the signal wave height and also the peak wave period. The top is the signal wave height and the bottom is the peak wave period. And the first year is just showing the mean for the 2020 for wave height WLT. And when you compare the root mean square error with that of DIA of WLT, you can see that we have just large errors in regions of high wave, in the Southern Ocean, the North and Pacific and Atlantic. But when you compare with the ML, we can see that this error is greatly reduced, like up to 7 times in some region. When you compare the Southern Ocean, the error is reduced up to 7 times in that region, almost zero in some place. And also, when you look at the peak wave period, the word I'm talking about here, just look at the Atlantic, we can see that our ML model reduces the error in the peak wave period introduced by DIA in the Atlantic and also in the Indian Ocean. So like I said, we'll be comparing our performance with era 5, and we compare the three parameterization of ERT, DIA, and ML, and against the analysis data from era 5, same with signal wave height and um, peak wave period. This is showing the global mean time series of that. What is you can see here is that the all parameterization captured the general variability observed in era 5, and you can see that the WRT and the ML model follows each other closely, and also follows the era 5 compared to the DIA. You can see this large possible bias in DIA, and also same thing can be said for the peak wave period. So our ML model is really doing a better job than the current DI approximation in wave model. So we also want to look at the importance of what we improved in the ML model compared to previous studies. Like we added additional input. The first is the depth. So we train our model with no depth, but we realized that the removal of depth shows no signal different, and this is because this is possible because the spectral energy and spectral nonlinear interaction that we used to train, we took that from the box region, which comprises of both the shallow water region and the deep ocean region. So even without including the depth, our training data already have a signal of difference between spectral and nonlinear interaction between shallow and deep water ocean. So most likely that's why there's no difference. So the depth we can actually do without depth, but I decided not to remove it because this is just um, I failed to mention that the spectral resolution is 50 by 36, and when you flatten it, it's like 1800 inputs. And then when you compare 1800 inputs of the spectral compared to one of the depths, you are not gaining any computational time. You're not doing anything. And this is showing when you don't include the group velocity. And you can see when you do include the group velocity, we have reduced model performance accuracy. So our addition of CG actually improved the model performance. But one thing that we find here is that when you remove both CD and depth, the model is still very stable, and they still even perform better than the DIA. But just like we have a better performance with that compared to our default model. Also, we talk about the customized loss function. So I'm going to be talking about first the customized loss function, why that is important. So we also train without using the customized loss function, just using the mean absolute error. So standard deviation equation is not there, and this is the result. You can see without using the customized loss function, we have a reduced performance. So the customized loss function actually improved the model performance, especially in like this IOU you can see from here. So anyways, this is still, like I said, it's still better than the DIA, but no, it's better than it's not doing very well compared to our default model, which is almost zero in most places. And also, I mentioned that we converted from action density in wave number direction space to spectral energy in frequency direction space, because the WRT was actually developed in frequency direction space and using spectral energy. That's why we did that, and that's also what the DI also did. They also approximated that in the frequency direction space. So we did that. So without doing any conversion, and then this is without doing any conversion, and also without using any conversion to from action density to frequency, we realize that you can see that our model blows up, the model becomes unstable. So it's not really conserving anything, and then the spectral energy actually grows. So conversion actually is important for training the model. stability. That's what I feel is responsible for our stable model and for improved performance, additional inputs. Now we'll be able to show that the first problem is we have a model that is doing better than the DIA. Now most of those things is actually because the previous study problem is that they have a model that is doing better than DIA, but the speed is actually slower compared to DIA. But now we need to look at the computational performance of an NML model. So we'll be comparing with the DIA, since that is the gold standard for time. And when you, like I said, the WRT compared to DIA is like 142 times more expensive than the DIA. And when we do our inference on CPU, the ML model is 3.2 times slower than the DIA. So we move to GPU for improved performance, and we realize that the ML model is just like 9% slower than the DIA on GPU. Then we further use half precision inference on GPU, and we were able to reduce that by half to get 4% slowdown on GPU. So with half precision, we just have only 4% slowdown, which is acceptable because and this is the first wave model with half precision inference on this. So we need to test if error may arise from our difference in mathematical precision between CPU and GPU, and also between the GPU and also the half precision inference. So this is showing here the root mean square error compared to WRT of the first one is our default model and on CPU, and the second one is on GPU, and then the third figure is showing GPU with half precision inference. And we can see here that we are not introducing new errors, and then we can actually go forward with the half precision inference as our standard model for the ML. So our mission has been accomplished. We have an ML emulator that matches closely the accuracy of the exact method at the cost of the faster approximate method. So it's fast and it's accurate. So summary, we develop a stable deep neural network for the exact nonlinear interaction in wave model to address the limitations and deficiency of the DIA. We only trained on, I failed to mention that we only trained on less than 10% of the global wave model. So we have we use 56K structured mesh grid points, and then we trade on just 3,000 points. And where we're able to generalize across all spectrum types. The inclusion of group velocity improve our ML model, and our ML model achieve 2 times better accuracy when you do a global wave spectral energy, but at some particular location is up to 7 times higher accuracy, for example, the Southern Ocean. We leverage the GPU computing capability with our precision inference, and we're able to just get 4% slowdown compared to DIA. And this our ML parameterization actually bridges the between accuracy and efficiency, so offering a promising alternative for improving wave model in operational settings and research purposes. Thank you.